Welcome to this tutorial on the management of tags in GNU Radio. I'm Morin and I will be joined by Lavarenne in the second half of this presentation. This tutorial contains several exercises and for each of them you will be able to work on them for 5 to 10 minutes. A correction file will be available about the halfway point. Let's get started. We will start this presentation by explaining what are tags and how they fit inside the data streaming process of the GNU Radio flow graph. And then we will put it into practice. We will begin that by creating a small flow graph to generate tags using standard library blocks. And then we will use this flow graph to create Python blocks that can first detect the tags and then use their different properties, such as offset and value. And finally, we will put all of this into practice using a more concrete example of the ADSB protocol. Okay, so let's begin by understanding what tags are. To do that, let's take a look at this animation. Here we have a very small flow graph, classical flow graph, with just a signal source, something that squares it, and a plot, a time sink. So we generate a sinusoid, and then we square it. That's a simple processing that we could have in GNU Radio. So if we now zoom inside the first buffer in this chain between the first two blocks, we can see that when the graph execution is started, we have chunks of samples, blocks of samples that are output by the source block. And each of these samples has a number, the offset. As you can see here, all of them are numbered. This number is absolute. It begins at the start of the execution and never stops increasing. And the receiving block also works on chunks of these samples. So these are the basic working of the work functions of the blocks inside of GNU Radio. The number scheme that we just talked about, the offsets, is independent from one buffer on one block to the next. And it depends on the rate at which the samples are generated. So now let's add tags to this stream. The tags are a way to add metadata to specific samples within a stream. And most blocks are able to propagate the tags they don't use to their output. If we zoom in again inside of the first buffer, we can see that the tags move in parallel to the main stream. They actually are just a data structure with 4 fields, beginning with the offset, which defines which sample the tag is linked to. And then we have the name and the value, which are user-defined. The name is also called the key, and it can be also used to filter the type of tag we want to listen to. And the value is, well, whatever we want to put inside. And finally, we have a source field that identified the block that first created the tag. And by default, most blocks propagate tags by copying the content of the input tag into their output and just adapt the offset to the new buffer at the output. But the task of computing the correct offset to copy the tag may be quite complex, depending if the rates of input and output is variable and maybe if there is multiple output and outputs to the block. So some blocks don't do it properly, or some don't at all. Now that we've seen what tags are in theory, let's get practical. We are going to switch to GNU Radio, and I'm going to start with a flow graph that's available on the tutorial page on the website. So we have, as a starting point, a very basic flow graph. We have just a signal source that outputs a cosine wave that goes into a throttle, and we can plot it with a time sink. And if we run it, we can see that we have just a simple sinusoid. Now what we want to do with this is to add tags to this stream. The first way to do it would be to add a block called stream to tagged stream. We can find in the stream tag tools section. If we open this block, and first of all, let's start with using it with floats. We can see that we can input it a tag key or tag name and packet length. If we say 100 in there, for example, and if we plug it inside of the flow graph, and run it, we will be able to see what it creates. So if I stop this flow graph, we can see that now we have the exact same sinusoid signal, but we have on top of that, at regular intervals, so basically every 100 samples, we have one tag with the key on the name packet length and the value 100. We can also see with this that the Qt timesync is able to display the tag, which is quite useful for debugging. And so the thing is, this stream to tag stream does not allow us to choose what the value of the tag is. It's always fixed to be the packet length. So in our case, we will not use this block, but we will use the tag strobe block. Here we go. So if we open the properties of this block, and first convert it to use floats, we can see that this time we can choose at which frequency we want to put a new tag. So if we say I want a new tag every 100 samples, and we can choose explicitly the key and the value that we want for the tag. So in this case, as a basic example, we will just put tag and maybe value. The key is expected to always be a PMT that contains a string, and the value could be also a PMT that contains the string, so in this case the string value, but it could be also a PMT that contains a number or a dictionary, a list, or pretty much whatever we want. If we select that, we have now the tag strobe that has one output and a signal source. If we just look at what's going on at the output of the tag strobe, we can see that the block outputs just samples with zeros and at a regular interval the tag that we want. And now we want to be able to merge the two streams, so have the sinusoid of the signal source and the tags of the tag strobe. So to do that, we will use the block tag share. That's presented like this. And so it has two inputs and one output. If we select this, what this block does is that it will just copy the contents of the sample that goes into the input, and it will share the tags that are present inside of the share input into the output. And so if we plot this, if we use it like so, we can see that now we have our sinusoid and the tags. Now to get a bit more interactivity, we will add a way to select the frequency at which we have tags at runtime. And to do that, we will add a range, a Qt range, like so, that we will call, for example, tfrec. With somewhat sensible values. And we will set the tag strobe to use it in the num sample parameter. And so now when we run that, we get, just as before, the synonym and the tags, but we can change with the slider the space between the tags. While we are at it, let's showcase a feature of the Qt timesync that's related to the tag. We can add a trigger based on the tags. And when we do that, it asks us for the name of the tag or the key of the tag we want to select. So in this case, it's a tag. And so when we have that, we can see that we all the time have the first sample be a tag. And then we can change and really see the change of frequency. Okay, so now that we've seen how to add tags with basic library blocks, we will get to the next step, which is create custom blocks, in this case in Python, and use the API to manipulate blocks inside of them. And so what we will want to have is at the output, add a new block, in this case a Python block. We will work with embedded Python blocks, but we could also use AUT modules with Python or C++. It would work the same. And so we will add this new block in there. And for the next step, we will modify these Python blocks. This can be done simply by opening the parameters of the block and selecting open it into editor. Okay, and if we open it, we can see that we have a default block that does basically nothing. It just copies what it has at input and it puts it at the output and it multiplies it by the parameter. And so what we will need to do is modify it to use at input the type of samples we want to have. So in this case, floats. And we will maybe just remove the use of this parameter. Okay, when we save this, we can connect it and run it. As expected, we have exactly the same value for the original signal and the modified one. Okay, so now that we have the basic framework to play with blocks, let's get back to the slides. So the first thing we want to do to play with tags is to first of all detect that we have tags. So we have two ways to do that, or actually two functions. Both of them work similarly. They both allow to filter by tag name or the key, and they both output a list of tags that are seen. The difference between the two is that the getTagsInRange function operates with numbers of start and finish of range that are absolute, so the row offsets of the samples from the start of the execution of the flow graph. And the getTagsInWindow function uses numbers that corresponds to the beginning and the end of the samples available to the current forward function. So in most cases, the getTagsInWindow is a bit more practical to use because you don't really need to know where you are since the beginning of the execution of the flow graph. Okay, so now let's get to the first exercise. The first task will be to modify the embedded Python block we just had so it can mute and unmute. So either copy what's at the input or just put zeros in this place, and start and stop muting this if a tag is seen as input. Don't forget to import pmt at the beginning of the Python file, so we can use the pmt.intern to filter with the tag name. You now have 5 minutes to work on this, and at the halfway point I will make available the correction file on the website. Okay, so now if we open the correction file, so tags embedded part 1, that's available on the website, we get this. And we can see that the block mutes and unmutes. Sometimes we get zeros and sometimes we get the sinusoid. But it's not really related to the actual position of the tags. So the next step will be to make it so that the muting and the unmuting happens exactly on the positions of the tag. And to do that, we will remind you that the tags that we get in the list of tags output by the get tags in range or get tags in window functions, they all are objects in Python or C++ that have the 4 attributes of the key, the offset, the value, and the source. So we can use this offset, which is an integer, to find out the position of the related sample in the stream. So let's get to this. I have 10 minutes to do this. And as before, at the halfway point, I will make available the part 2 correction on the website. Okay. And now if we open this part 2 correction from the website and run it, and maybe hide the original signal, we can see that now we have truly the mute and unmute functions that happens exactly on the positions of the tag. And if we change the frequency of the tags, we can see that it does match. The muting and unmuting process is still exactly on the tag positions. Okay. And now the third exercise will be to play with the values of the tag. And to do that, we'll just do a bit of setup inside of this. And we will make it so that the tag strobe has a value that is a number, first of all. So we can do this by putting as a value not pmt.intern that works on strings, but in this case pmt.toPmt that is able to operate on most Python types. And we just put maybe 10. If we run this, we can see that the value of the tags, maybe I'll stop it, is now 10 as we wanted. And to have it be a bit more dynamic, we will add a new range that will allow us to select the value of the tags at runtime. So if we add val, between maybe 1 and 100, that's fine. We can now use this new parameter in there. And when we run it, we have as a base the tags that have 50, so that's to be expected. And when we change the value of the tag changes with it. Okay, so now that we have a bit of setup done, the next task will be to have the block start muting when a tag is received and mute for as many samples are in the value of the tag. So for instance, if the tag says 50, mute for 50 samples after the reception of the tag. So now you have 10 minutes to do this, and as before, in the halfway point, you will have the part 3 file available on the website. So let's check that it works properly. If we open the tags embedded part 3 and that we run it, I will add a trigger to the tags so that we can see a bit better. Okay, so now that we always trigger on the position of the tag, we can see that if we increase, for example, the tag frequency, we have tags a bit less often. And if we zoom in and just plot the samples exactly, if we count them, we can see that we have truly 10 samples, which is the value of the tag. And if we change the tag length, we can see that the number of zeros changes with it. Okay, so now that we've seen how to read the two main fields, which are the offset and the value, I will leave the floor to Thomas, which will talk to you about how to write tags in custom blocks, as well as the operation of several other types of basic standard library blocks.
Okay, thanks to Cyril for this first part of the tutorial. I'm Thomas Lavarenne, and we will now take a concrete example in which the tags will be used to preprocess the ADSB frames. But first we will need to understand a little what is ADSB. So what is ADSB? ADSB, Automatic Dependent Surveillance Broadcast, is used in civil aviation to transmit parameters of the airplane to the ground stations or to the airplane. You can find everything on the mods.org website. Let's watch just a moment. Okay, click on read the 1090 MHz reader. Here you will find absolutely all the information about ADSB frames and how all the different parameters are implemented, if you ever want to decode them later. So just have a look to ADSB Basics. In ADSB Basics, we can find the frequency of 1090 MHz. We also find that the frame is 112 bits long, and we find that for civil aviation, the message starts with a downlink format with value 17. It corresponds to 10001 in binary. That's for the first 5 bits of the message. Okay, let's go back to the presentation. So, the important parameters are ADSB use amplitude modulation at 1090 MHz, and ADSB frame is 112 bits. It uses pulse position modulation, and bitrate is 1 megabit per second. Now, let's take a closer look at the start of the frame. The frame starts with a preamble of 8 microseconds. Then we have the downlink format, DF code, with value 17. We can see that logic 1 is transmitted by varying the amplitude from a high state to a low state in the middle of the duration of a bit, and vice versa for a 0. We can consider that it's a bit similar to the Manchester coding. But what interests us more precisely now is that by choosing the sampling frequency at 2 MHz, we can obtain a signal containing 2 samples per bit. Okay, now it's time to practice. You have a file, a GRC file, adsb2to.grc, which is already pre-completed. You can use the instructions below to observe the ADSB frames. You can open it with your GNU Radio. We will let you 3 minutes to observe and play with this file. Then we will look together what's going on more precisely. Okay, here we go again. Let's look together what's going on. Here we have the file source, the throttle, the complex to max squared that inputs the amplitude, the threshold that outputs only 0 or 1, and the time sink. If you run the flow graph, we see many signals. As you can see, it's very difficult to synchronize and visualize one ADSB frame. We have many signals, but it's very difficult to catch one ADSB frame. So we are going to see that the use of tags will be really helpful for us. For that, you have to introduce a new block, the correlate access code tag. The correlate access code tag is a block that will search for a pattern in the stream and attach a tag with a specific name on the next sample. For that, you need to indicate the access code, that is a pattern that you're looking for. The threshold is the numbers of error you accept in the access code, and the tag name. But now it's time to practice again. So I will let you read the exercise and we will meet up in a few minutes for the correction. Okay, let's go for a quick correction. Here we can find the access code 10100010100000, etc. Up to the DF code. Simply copy and paste the access code in the correlate access code block. Threshold is 0, tag name is packet. Validate. In the properties of the timesync block, it's possible to set the trigger to tag, or you can let it to free and specify it later. First, you need the control panel. Then, specify trigger to tag and enter the tag name. Now you can adjust a little the visualization to see clearly the ADSB frame. It's really much better than before. Now we will go even further in the use of tags, and we will use a new block to save the data of each frames in separate files on the hard disk. For that, we will use the tagged file sync. To learn how it works, just read the wiki. A file sync that uses tags to save files. The sync uses a tag with a kburst to trigger the saving of a burst data to a new file. If the value of this tag is true, it will open a new file and start writing all incoming data to it. If the tag is false, it will close the file. So, we have to write a block that puts a tag burst with value true at the beginning of the frame and another tag burst with value false at the end of the frame. Next and latest exercise, I let you read and we will meet up in a few minutes. Okay, let's start by adding the tagged file sync block. And then we have to set the input type to byte. The GRC file provided contains a pre-completed Python block called ADSB divider. Open properties and open the code in editor. Use default. Okay. In the init, we will see that there is already a parameter which is a tag name, namely packet. Now we will complete the code in the work method. In the list of usual functions, let's get the one that allows you to retrieve the tags. Get tag in window. Copy and paste all the line in the editor. Tags equal self dot get tags in Windows. The input stream is 0. The start of window is 0. The end of window is the length of the input items, len input items 0. The tag name is packet. Here it's the parameter in self.tagname. Now we have to launch a for loop which will process all the tags. For in range len tags, a burst tag is added to each packet tag with the method addItemTag, with the output stream, the offset, the key, the value, and the source. Self.addItemTag, output stream 0, the offset of the tag, tags dot offset, the key is the name burst, pmt.intern burst. The value of this burst tag is true, so we write pmt.pmt_t. The name of the source is optional. The function will add a name by default. So we copy this line, pmt dot. We copy all this line. To add a second burst tag at the end of the frame, but the value false. It's necessary to specify the position of this tag. The packet tag was placed after the preamble on the DF code. If we want to recover all the frame, we must include the 5-bit DF code, so an offset of 10 or 11 samples for the first burst. The second burst, as we know that the message is 112 bits long, we add an offset of 224 samples. All we have to do now is save and check if everything is working. Okay, save. Now validate. We activate the block and connect it directly to the correlate access code block. Then to the time sync, and finally to the tagged file sync. Oh, it may have one or more errors. Let's look at the debug. It seems that we have an indentation problem. So let's go fix that in the code. maybe here. Okay. Here. And here. Okay, it looks good now. Look what happens when you execute the flow graph. Set the trigger to tag, indicate the name packet. Okay, it looks good. We see the burst tag with value true at the start of the frame and the burst tag with value false at the end. Well, let's take the opportunity to definitely adjust the time sync, set the trigger to tag, add a delay of 20 microseconds, and indicate the tag packet to trigger the stream. Okay, execute. Okay, everything works as expected. So, before finishing this tutorial, I offer you an interesting modification. So as not to have to enter the values of the offsets manually in the code, I think it's better to add two parameters, length and preamble, that the user can enter in the block directly in the GRC file. Okay, so open the code, open in editor. 11 is the preamble, so we'll name it self.preamble. Here too, self.preamble 224 is the length of the frame, so we will name it self.length. And the same principle as self.tag name, we add self.preamble equal preamble and self.length equal length. And finally, you add them in the init. Preamble equal 0 to initialize, length equal 0. We save the file and see if it works. Okay, we can indicate here the preamble and the length. Execute the flow graph. Okay, everything still works. But now let's see if the tagged file sync also works. Let's go in the home folder and we see a lot of files that are created continuously. Each size of file is 224 bytes, which is the expected size, because each value, 0 or 1, is stored on 1 byte here. Well, the tutorial is finished. Thank you for your attention. If you have any questions, you can join us in the chat or leave them in comments. In conclusion, and to wait until the chat resumes, here is a possible continuation of this part of the tutorial illustrated here. An external processing of the recorded files